Okay, all this is the last session for PHYS30141. In this session, we'll be going through the week 10 problems. As I indicated in the email, this is one of the more important sessions to go through carefully. Synchrotron radiation is one of the most important areas of electromagnetic radiation. And these questions are designed to illustrate some of the facts that you need to be aware of when doing calculations of synchrotron radiation emission. So we're going to use as our example for the week 10 sheet, the diamond light source, and some of the calculations shown here are also included as examples in the lecture notes and in example sheet 5, but I'm varying them slightly to help illustrate some different pieces of our puzzle when we do calculations. So we're considering the UK diamond light source, and there are a number of electron storage rings which are used to create synchrotron radiation, and they are used to create X-rays, and those X-rays are used for a variety of scientific disciplines that include things like X-ray diffraction, spectroscopy, and things like that. And if you have a look at the YouTube playlist, there were several videos that showed walkthroughs through a few of these facilities. There are around about 50 of them around the world, and each one of them costs in the region of a few £100 million to construct and operate. These facilities are the mainstay of X-ray science around the world, and the videos will show you, roughly speaking, what these accelerators look like. And in terms of the synchrotron radiation production, one of the key things to bear in mind is that the dipole field, which is bending the particles, bending these electrons into a closed path, those dipoles are not there everywhere. Okay, it's not a homogeneous field in a real accelerator. So these questions are there to illustrate that. So we're going to look at diamond, and if we look at our question sheet on the left, we imagine the diamond storage ring has electrons circulating, which means they're orbiting repeatedly with a kinetic energy of 3 giga-electron volts. So their total energy is very slightly more than that. It's 3 giga-electron volts plus half a mega-electron volt. So it's only very slightly above 3 GeV in total energy. And the electrons are passing through dipole magnets in which a magnetic field of 1.4 Tesla is present. So when we say it's passing through the dipole magnets, it's passing in the gap between the north pole and the south pole of the magnets. And there's a vacuum vessel that allows the electrons to circulate within a region where there is no atmosphere, where the pressure is much less than normal atmospheric pressure, so they don't hit anything as they're going round. And the electrons are repeatedly going round and round of the order of 1 million times a second. They make an orbit in about 1 microsecond or so. And a single electron may survive within the accelerator for upwards of 10 to 12 hours. Emitting synchrotron radiation as it circulates. So an initial amount of charge will be kept circulating for a very long time in these electron storage rings. And the videos will show you those components so you can see how that works. Now in question 1, we're going to first consider a homogeneous field. So rather than a real electron storage ring where I have dipole magnets which are separated and they have drift spaces between them, and in fact in those drift spaces there are also other magnets which are used for focusing, which we won't consider here, but those magnets don't give rise to any synchrotron radiation, or very, very little anyway. To begin with, we're going to think about a homogeneous field of 1.4 Tesla. So our first calculation is to see what's happening when there's a homogeneous field. Now let's look at the answers. So one of our key equations that we obtained from this right-hand equation, we can obtain by balancing the centripetal and magnetic forces and taking account of the relativistic nature of the electrons. We can calculate the radius of curvature r in terms of the beta and gamma factors of our electron. Remember that at 3 GeV, the gamma factor is many thousands, right? The radius of curvature is given by this equation on the right directly, but we can also re-express it in terms of the momentum, P. Remember the momentum P is beta gamma m0c, right? And the rigidity BR, remember the rigidity BR is is the product of the magnetic field and the bending radius, and that's given by the momentum divided by the charge, P over Q. So P and Q are properties of the particle. Q is the ability it has to be bent, and P is its momentum, which is its rigidity against being bent. So BR, that product, is known as the beam rigidity. So you can see that if we double the magnetic field B, we halve the bending radius for a particular combination of P and Q. Now, for relativistic electrons only, we can use this simpler form that if we have a certain beam rigidity, BR, and we multiply it by 0.2998, and you can recognize that hopefully as being to do with 2.998 times 10 to the 8 meters per second, BR times 0.2998 is the same thing as the energy of the electron in GeV. Remembering that this energy, it doesn't really matter much if it's the kinetic energy or the total energy, because they're almost the same value for very relativistic electrons. So we can use either of these two formulae. We'll basically get the same answer. A 3 GeV electron has a gamma factor of 5871, and its beta, its relativistic factor, is basically 1. It's going at the speed of light. So the bending radius in a 1.4 Tesla field is 7.15 meters. Now, if I have a homogeneous 1.4 Tesla field, then the path length that the electrons go around as they execute one orbit, this circumference L here, is 2 pi r. So 2 pi r is the same as the circumference if the field is homogeneous, if it's the same everywhere. So in this case, of course, it's 44.92 meters. So the orbit time, the time it takes for the electrons to execute one orbit, is of course just that L divided by the speed of light, which is about 150 nanoseconds. So that's the first part of our answer. Calculate the following: orbital radius, orbital time, and circumference. So the orbital radius, 7.15 meters, the circumference, 44.92 meters, and the orbital time, 150 nanoseconds. Now, from these numbers, we can calculate the radiation power, the critical photon energy, and the energy loss per orbit. So let's calculate that. Now, in the notes, we can use a variety of formulae from equations 634 to 653, but when we calculate them and we plug in the numbers carefully, we find that the emitted power should be 1.07 microwatts. The critical energy is 1.34 times 10 to the minus 15 joules. And when we convert that into keV, and we really ought to convert it into keV, we see that it's 8.39 keV. So we remember that the critical energy is defined as being the photon energy above which half the power is emitted and below which half the power is emitted. So the critical energy is a typical energy for the photons. Okay, so it's similar to our ES value in the notes. Okay, it's lower than that, but the ES value we obtained by doing a scaling argument based on relativity. Remember, we said that the critical energy was done with a more careful argument about how many photons are emitted at different energies, and that critical energy here is 8 keV. And if you calculate the wavelength, you'll see that that is below 1 angstrom. And that's the reason why the diamond electron storage ring uses electrons with an energy of 3 GeV. 3 GeV electrons, which is straightforward to obtain, 1.4 Tesla magnets, which are also reasonably straightforward to obtain, allows us to generate photons with a typical energy of 8 keV. And above the critical energy, remember that each photon above the critical energy carries a great deal of energy with it. So there are relatively fewer photons above the critical energy than the many photons that there are below the critical energy. Okay, so the same amount of energy carried by one EV photons, of course, is many more photons than the same amount of energy carried by one high energy photon. So we see a very steep fall off in the number of photons in a given photon bandwidth above the critical energy. Okay, so there is that shape is shown in the notes, and I'll try to find time to show that at the end of this session. Now, because many more photons are made at lower energies than at the higher energies, the average photon energy must be lower than the critical energy. And as it turns out, there is an approximate form, which is, this is the form you should remember. The approximate form is that the average photon energy is about the critical energy divided by 3. So there's an exact factor given in the notes, but it's about 1/3. And when we plug that in, we find that the average photon energy is 2.8 keV. So we'll come back to why that's a useful number in a moment. Now, the energy loss per turn, remember the energy loss per turn is the energy lost from an electron as it executes one orbit. One turn is one orbit. That's the energy loss to any different possible energy photons. Remember, the electron is emitting many, many photons at low energy and relatively few photons of high energy. Integrated across all those energies, the energy lost in one orbit, of course, must be equal to this power. That just comes from our scaling of the Larmor formula, times the orbital time that we already calculated, that's 150 nanoseconds. And in this case, it's a reasonably neat number. It's about 1 MeV. And of course, as we decrease the electron stored energy, imagine we have 1 GeV electrons instead of 3 GeV electrons, the energy loss per turn would be much, much lower. So that's the energy loss per turn, and it's conventionally labeled U0. So next thing to calculate is, if that's the energy loss, what fraction of the initial energy of the electron, which we label E. Now, I realize that there are a lot of E's floating around, so you have to keep an eye on which one we're talking about. So our nomenclature in this particular example sheet is E is the energy of the electron, E critical is the critical energy of the photons, and E gamma with these little brackets around is meant to indicate the average photon energy, and that should be consistent with the nodes. So if E is 3000 MeV, that's our stored electron energy, and U0 is the energy loss per turn, well, obviously that factor is about 3000, and that means it will take something like 3000 orbits for the electrons to lose all their energy. So that means the electrons will damp themselves. They emit radiation and they will spiral inwards. And in fact, because the beam pipe within which the electrons are circulating is actually quite small, it's only maybe 70 millimeters across in diamond. Actually, the electrons only have to lose only a small fraction of their energy before, as they spiral inwards in that constant magnetic field, they will eventually hit the walls of that vacuum chamber, and they will then plow into these are typically aluminium or copper. They will plow into the metallic walls and they will generate Bremsstrahlung radiation as they do so. And of course, we'll look at Bremsstrahlung in the following example sheet. Okay. Now, in reality, the electrons don't really do that because, of course, we feed in a voltage. There is a voltage that is replacing the lost energy. So as well as the electrons radiating energy, U0, once per orbit, we feed in radio frequency power, and that power is delivered by what are called RF cavities, radio frequency cavities. And the effective voltage delivered to those cavities must be equal to this energy loss in order for the energy of the electrons on average to remain a constant. And that's what we're doing. We are storing the electrons, hence the phrase storage ring. We're storing the electrons and maintaining them at a constant energy. So the energy fed in, the RF voltage, which is effectively delivered to the electrons, which is re-accelerating them, must be equal to U0. Okay, so U0 is an energy in MeV, but the voltage must be 1 megavolts in volts. Okay, so that the energy delivered to each electron when passing through that voltage is obviously equal to QV, where Q is the electronic charge. So that is the damping value. Okay, 3000 turns in the case of these electrons. Now, the damping time that goes with that is the amount of time it takes for the energy to be dissipated. You can see here is about 0.5 milliseconds, 0.45 milliseconds to be exact. So there is a damping time associated with that loss of energy. Now, The next part of the question, it says here, this is question 1, it says calculate the number of photons emitted per orbit. Now we can calculate it a number of ways. We could calculate it based on the critical energy, but the normal way we do it is by calculating it based on the average photon energy. So we're saying what is the typical number of photons emitted per orbit if those photons each have a typical energy equal to the average energy. That's the most natural way to calculate this number. And that number of photons, of course, must be equal to the energy loss divided by the amount of energy in each photon. And if we calculate that, it's about 360. We can do that calculation in another way. There's another formula given in the notes that we derived, which is a dimensionless quantity. It's 8 pi over 3 alpha gamma. And again, this is only an approximate form, and it's an approximate form because we made the approximation up here. Where did we say that was? Oh yeah, we made the approximation that the average photon energy was the critical energy divided by 3. That number is not quite true. It's approximately true, and therefore this formula is also approximately true. But let's do that formula in our heads. Gamma is about 5,800. Alpha is about 1 over 137. So this is 6,000 divided by about 100 or thereabouts. Okay, so that's about 60. And 8 pi over 3, well, pi and 3 are about the same. So that's 60 times 8. It's not far off being about 400 or so, which is what this number is. Okay, so if we put these numbers into our calculators, we see it's about 359. Okay, so you can see that the number of photons emitted per turn only depends on the electron energy through gamma. It does not depend on the magnetic field. Why is this the case? This is because if we were to have a lower magnetic field, then the rate of photon emission would be lower, but the electrons would be traveling for a longer time, through a longer distance through that magnetic field in order to execute one orbit. So those two terms cancel, and hence we only see the electron energy appearing in our number of photons. Oh, as well as when the magnetic field falls, of course, the typical photon energy also falls. Okay, so that also appears in this derivation. Okay, that's question 1. And as I said, again, if any questions, please shout out. Okay, let's move on to question 2. So question 2 is the real accelerator. So in question 1, we had a homogeneous magnetic field, B, but in a real accelerator, those regions where the magnetic field exists are separated. So we call those regions dipoles because they have a north and a south pole, a dipole. And in between the dipole and the next dipole, there is a region where there is no magnetic field. So this is called a drift space because, of course, the particles are not experiencing any force, so they simply drift from one dipole to the next. And I know it's indicated here in this cartoon picture that there's some curved path, but of course, the electrons must be traveling in a straight line from one dipole to the other. Now, there are some extra little bits and bobs. I mean, the magnetic field doesn't fall immediately to 0 at the end of the dipoles, and there are other devices in between each dipole and the following one. There are quadrupole magnets and other magnets, but these don't emit a significant amount of synchrotron radiation from the point of view of this calculation. So that's our picture. In a real accelerator, only a small fraction of the accelerator actually contains dipoles, and that's usually the case. So as the electrons travel through the dipole magnets, as they travel in that gap between the North Pole and the South Pole, they see a magnetic field of 1.4 Tesla, and that's what causes their acceleration and causes photon emission. And as they exit the dipole magnet and they enter the drift and start traveling in a straight line, they stop emitting radiation. There is no photon emission in the drift spaces. So let's examine what happens in that photon emission. So inside the dipoles, we assume, of course, that the magnetic field in these dipoles on the right is 1.4 Tesla, the same as in the homogeneous field case on the left. Inside the dipole magnets, the bending radius of the electrons is the same as it was before, Br equals P over Q. And I realize, by the way, I should mention that occasionally I will swap the letter R and rho. Rho is often used for bending radius, and I may have done that in a couple of places in the notes and in the example sheets. So you might see B rho rather than Br, but of course it's the same quantity. So inside the dipole magnets, the magnetic field is the same, So therefore, the bending radius is the same as it was in question 1. And when the photons are emitting, they're receiving the same acceleration. So therefore, the critical energy and the average photon energy are the same. So it's a fairly easy calculation. So the rate of photon emission while the electrons are within the dipoles is exactly the same as it is in the homogeneous case. However, the photon emission in the regions where there is no magnetic field is now 0. So whilst the rate of photon emission in the dipoles is the same, the average for all the time the electron is going around in orbit, that average photon emission rate must be lower, because sometimes the electrons are not emitting photons. But if we think about the amount of time that the electrons are spending in the dipoles per orbit, that amount of time is exactly the same as the amount of time the electrons must be seeing a magnetic field during one orbit in the homogeneous case. So the total amount of energy loss in one turn must also be the same. So regardless of whether the field is homogeneous or divided up, as long as the magnetic field is the same, the energy loss per turn is also the same, because we have the same total 2 pi of bending angle. But as we said, because we now have drift spaces, the average power is much less potentially than the power radiated during the photon emission within the dipoles. Okay, because much of the time the electrons are not inside the dipole. So let's calculate that. So let's calculate it. So just as we had in question 1, the total path length that the electrons have within the dipole magnets must be the same as in the homogeneous case. It must be 44.92 meters of that field in order for the electrons to go round in a circle. We don't need to know how many dipoles there are. We don't need to know how long they are. The fact that the electrons are bent round into a circle tells us how much. So in the case of diamond, as it turns out, there are 48 dipoles, but there could be 24 dipoles. There could be 4 dipoles. It doesn't really matter. That total length must be the same in order for the path to be a circle. Well, sorry, for there to be a closed path, I should say. So that's the total path within the dipoles. Now we're given in the question that the circumference of diamond is actually 561.6 meters. So we can see that the circumference of the accelerator is very, very much larger than that L equals 2 pi r value. So the average power is much lower by about a factor of 10 compared to the peak power. So this P value is the same as we had before. That's 1 microwatt. But the average power is just L over LC times that peak power, the value within the dipoles, and it's about 86 nanowatts. So that's where that number comes from in the example sheet. Now, on the chat, there's a question which is, why does diamond use 48 dipoles in particular? Yes, there's many reasons. The reason that many dipoles are used is because diamond is composed of a series of achromatic bending sections. So this is a realm of particle accelerators called accelerator physics. This is my research area. In fact, I actually did the diamond storage ring design some years ago, so I know this particular design quite well. By having a certain number of cells, so there are 24 cells in diamond, each one containing 2 dipoles, we restrict the spread of the electrons within these drift sections so that we can place other emitting devices. So I haven't mentioned those for simplicity, but there are in fact other emitting devices placed within the storage ring, but we're simply ignoring that for the point of view of this calculation because it just makes it more complicated. Okay. So this average power here in the dipoles is correct, of course. Okay. So the average power is lower than the instantaneous power emitted within each dipole. So U0 is the same. Now, because U0 is the same, and because the critical energy is the same, and the average photon energy is the same, N gamma, the number of photons emitted per turn, per orbit, must also be the same. So all those numbers are the same. The only thing that changes is the average power, because sometimes the photons aren't emitting as they go in through those drift spaces. So the key point to remember in all of this is that we calculated the bending radius in the dipoles, but that has absolutely nothing whatsoever to do with the actual circumference of the accelerator. The bending radius is due to the magnetic field in the dipoles. It's not a feature of the whole accelerator, and that's true for any accelerator. This could be the Large Hadron Collider. It could be an electron-positron collider. It could be anything like that. Okay. Here we've talked about it in terms of the synchrotron radiation accelerators, but electron-positron colliders have the same issue, that you get very strong synchrotron radiation because these are electrons. So let's look at that. We'll move on now to question 3. So in question 3, we now consider diamond, but now we're going to circulate positrons within the accelerator instead of electrons. So we're not going to worry about how those positrons might be generated. It turns out that's much more fiddly to do than to generate electrons, but there have been these synchrotron radiation facilities constructed using positrons as the circulated particle. So let's look at how that works. Here's question 3. So question 3, we answer it in the following way. The positron mass is going to be equal to the electron mass. The positron is the antiparticle of the electron. The difference is that the charge is positive and not negative. So if we wish to circulate positrons in this particular arrangement of magnetic fields, and again, you should look at the YouTube videos, and that will show much better than I can what that arrangement looks like. You'll be able to see the dipole magnets, and in the intervening drift spaces, you'll be able to see quadrupoles. In fact, the drift spaces are so filled up with quadrupoles and other equipment that they don't even look like drift spaces. Okay, so just look out for that. But in order to circulate these positrons in the same arrangement of magnetic fields, we must do one of the following. So we either do this. So imagine here is my dipole magnet, and the magnetic field. I have a north pole at the top, sort of out of the page, and I have a south pole at the bottom, on the underside of the page, as it were. And the electrons are going left to right. And I think I've remembered how to do this calculation this way around. The electrons will be bent to the right by that magnetic field. So this is the dipole magnet, and you have the drift spaces before and after. In order to circulate electrons through the same magnetic field, again, the magnetic field is still pointing into the page, a positron is bent in the opposite direction. So in order for it to execute the same overall path through this arrangement of magnets, it must be going the other way. So it must be going right to left instead of left to right. So of course, in order to create that situation, I will need to have some way of getting these particles into the storage ring, and that's obviously called an injection process. We inject particles into the storage ring. I must have some arrangement where I can inject those particles so that they travel in the opposite direction. So obviously we're not going to talk about injection here. That's a matter for another day or for another course. So you can see it's perfectly possible to have the same magnetic field simultaneously bending electrons clockwise and bending positrons anti-clockwise. So I can have simultaneously stored electrons and positrons passing by each other, but just going in opposite directions. And as it turns out, most often they have very little chance of striking each other unless I squeeze their transverse sizes to be very, very small, so that we maximize the likelihood that they will be close to each other. So most of the time, the transverse electron beam sizes are quite large, and they can quite happily overlap each other as they go past each other. They can cross each other without interacting in any significant way. So this is what we call a collider. An electron-positron collider has electrons going in one way and positrons going in the other way, and they are stored for long periods of time. And at particular locations, we focus those electrons and positrons so that they then interact with each other and collide. And those, of course, are called the collision points. And the puzzle for you to wonder about is in the Large Hadron Collider, which no doubt you've heard about. The Large Hadron Collider does not store protons and antiprotons. It stores two beams of protons, right? So it stores two beams of protons which are going in opposite directions. And by looking at this picture and thinking about that, you'll have to figure out what must be the arrangement of magnetic fields so that the protons going in opposite directions what magnetic fields must they be bent by in order they can be going in counter-rotating directions. Counter-rotating meaning one beam of particles goes clockwise and the other beam of particles goes anti-clockwise. So that's one arrangement. Now, let's say I can't be bothered to build a new injection system just for the positrons. What else can I do to store the electrons? Well, what I can do, of course, is I can just flip the signs of all the magnetic fields. So by swapping the connections on my magnet, remember these electromagnets, as you will see on the videos, these electromagnets, the field is excited by a coil, a conducting coil, usually copper. And by swapping the positive and negative power terminals, I can make the magnetic field go from pointing down to pointing up. And of course, in that case, and of course, I need to reverse the polarities of all the other magnets in my accelerator, the quadrupole magnets and other devices. And when I do that, I can use exactly the same arrangement of magnets in order to bend my positrons in the same direction. So by swapping the current from I to minus I swap the field from down to up, and now I can store positrons, but now these positrons are also going clockwise. So that's just a preamble to describe how positrons can be stored in a storage ring. But what about their emission? Well, that's actually pretty easy. Okay, how is the positron emission different from the electron emission? Well, the important thing here is all the magnetic fields, as we can see, are the same. All the magnets are the same, and the mass is the same. So for the same kinetic energy, which must be true to have the same path through the magnets, everything about the positron emission is identical to the electron emission. The power, the energy loss per turn, the critical energy, and the average photon energy, and so on. Everything is the same. So that considerably simplifies calculations with positrons. Okay, any questions before we go on to the last question of today? Okay. So our last question, we're going to go back to protons. So we're going to go back to considering protons, and we'll go back to looking at a homogeneous field again. So we're going through a homogeneous field of 1.4 Tesla, and we're being asked again to calculate the same things: orbital radius, orbital time, and so on. Now, the important thing to realize here is some of our shortcut formulae, particularly this beam rigidity equation here, which was basically the energy in GeV is about 0.3 B rho or BR. This only applies for electrons. In fact, it only applies for ultra-relativistic electrons. So we certainly should not use this for protons. So watch out for that. We have to go back to our basic equation, which is the bending radius for a given particle with rest mass m0 and charge q moving perpendicular to a magnetic field B. So that's our bending radius. And we need to now calculate our gamma and beta factors. And as we recall from the notes, gamma is about 3 plus the rest mass divided by the rest mass, because our kinetic energy is 3 GeV. So this is the same kinetic energy, but now the gamma is massively different. It was 5,000 before, and now it's about 4. Beta, for this gamma factor, is not quite 1, but it's pretty close to 1. So you could almost get away with using beta equals 1 in our calculations. We'll see that's not quite true, but let's go on with that. So the first thing we do is we calculate the bending radius. The bending radius is 9 meters, which is quite remarkable. Even though the proton is 2,000 times heavier, because its mass hasn't increased by very much, the bending radius is not all that different to the bending radius of 7 meters that we had in question 1. That surprises a lot of people. Now that number changes, of course, quite a lot as the proton goes up in energy. So if we had a 10 GeV proton compared to a 10 GeV electron, the difference would be bigger. So because the bending radius is reasonably similar, so is the path length through that homogeneous magnetic field. It's 57 meters now rather than 45 meters, but it's not massively different, even though the proton rest mass is very different to the electron rest mass. That's why this is an interesting question. I hope you agree. Now, the orbital time, of course, the velocity is not quite the speed of light. So we need to use that beta factor, but we'll see that most of the orbital time difference is basically to do with the bending radius and not really to do with the difference in velocities. So again, the orbital time here is 197 nanoseconds instead of 150 nanoseconds. And that's mostly to do with the difference in the bending radius, not really to do with the difference in speeds. So it's not far different. So let's calculate the actual radiated power in that magnetic field. So here's where all the big differences come from. So we use our basic definition for the emitted power. Remember, this is the emitted power during passage through a magnetic field. And we use the same formula we had before, b to the fourth, gamma to the fourth. We need to use the square of the electronic charge and the bending radius squared. So you see that 1 over r squared is slightly different to what we had for the electrons. But the main effect is this beta gamma term, which is hugely, hugely different. It's so different that you just need to be a little careful when you calculate it. So you can see if I separate out the beta to the fourth and gamma to the fourth factors, the gamma to the fourth value is about 311. And that should be compared with the 10 to the 11 or so factor that we had for electrons. It's massively, massively different. The beta factor is rather less important. I mean, it's around about a 10% effect. If I don't include it, if I forget to include beta, I maybe make a 10% error. That's not such a big deal. So the emitted power here is about 1.5 10 to the minus 19 watts. So let's calculate that in terms of energy loss per turn. The energy loss per turn is, again, that power times the orbital time. We said the orbital time is not that much different for these protons than it was for the electrons. So all of the differences in the power, and the emitted energy in one orbit is 10 to the minus 26 joules, which is about 10 to the minus 7 EV per orbit. So rather than being a million EV, it's 10 to the 15 times smaller. It's hugely, hugely smaller. We also calculate the critical energy. And again, we have to use our basic formulae, which is 3/2 h bar c gamma cubed over r. And when we calculate it, the critical energy of the photons is also much, much smaller. So remember before that when we had electrons with a kinetic energy of 3 GeV, when they move through a magnetic field of 1.4 Tesla, they emit X-rays. When I have protons traveling through the same magnetic field and they have the same kinetic energy, they emit radio waves, right? 10 to the minus 6 EV is very, very long wavelength radiation, about 1 million times longer than the wavelengths of light. So the average photon energy is still the same, 8 times 10 to the minus 7 EV, but now compare these two numbers. The energy loss per turn is now smaller than the average photon energy. So that tells you that the number of photons emitted per orbit is less than 1. So these protons are only emitting a photon on average once every 4 orbits as they go round and round. It's a very, very small number, and we calculate it the same way we did before, either by looking at the energy loss per turn and the average photon energy, or just using our dimensionless formula. Okay, so how long will these protons last? So we saw before that the electrons will radiate away all of their energy in several milliseconds. How long do the protons last? A 3 GeV proton, if it's emitting 1.8 times 10 to the minus 7 EV per orbit, will survive about 10 to the 16 orbits. That's a lot of orbits. So the protons, if I calculate the length of time that is, that means the protons will circulate without needing any voltage applied to them for about 100 years. So obviously something else will happen to them in the meantime. They'll strike obviously residual gas, or there may be a fault in the magnet or something like that, right? They can't possibly go for 100 years. But the message here is that the 3 GeV protons are coasting. They're emitting effectively no radiation. They do not damp. We've shown in this calculation that 3 GeV protons do not emit any significant synchrotron radiation, so I can ignore that when I consider their motion. Whereas the same energy of electron emits a great deal of synchrotron radiation, so I have to consider that when I consider modeling the motion. And of course, this also tells us why synchrotron radiation facilities use electrons or positrons, but do not use protons. It's also another reason why particle colliders at very high energies, more often than not, will try to use protons rather than electrons, because as you increase the energy of your electron that's being stored, if you double the electron energy, you can see that you get 16 times the synchrotron radiation power, and that becomes prohibitive to replace if you try to go to ever higher electron energies. And that's why the Large Electron Positron Collider, which had a circulating electron energy of about 100 GeV, had very, very large synchrotron radiation powers. Whereas the Large Hadron Collider, which circulates protons at an even higher energy of several TeV, the synchrotron radiation emission there is very, very small. So to get to the very, very highest collider energies, it's actually easier to use protons than electrons from the point of view of the synchrotron radiation. But as we saw above, if we look at the amount of effort required to bend the particles, as the protons gain mass at higher energy, they will become more similar to electrons in terms of the difficulty required to bend them into a closed path. Okay, so that concludes the answers to week 10. So hopefully you're able to work through them. And in the next worksheet, week 11, I have asked some questions about bremsstrahlung and about Cherenkov radiation. Now, there won't be a live session next week because this is the last week of term, but I will put up worked answers for that worksheet. But hopefully that'll be a lot easier and a lot less time consuming to do. Okay, are there any other questions for today? Don't hear anything. Okay, thank you so much for your time. If you have any questions in the meantime, please ask on Piazza. As you hopefully have seen, I'm trying to process through all the questions, and I'm making clarifications in the notes as I do so. So good luck with the examinations, and good luck, and have a very good Christmas break. You've all obviously earned it. It's been a particularly tricky semester, and I do hope you've enjoyed this course, and I wish you good luck for the rest of your studies.